2211, Section B, Lab 1, Constant Velocity. For introduction, the purpose of this lab is to record the motion of a real object moving in a straight line, use tracker to measure position versus time from a video of our marker, build a computational model using Newton's second law, compare the experimental data with model predictions. The main result is the object moved at a constant velocity, and the net zero force model matched the data closely. So the physics principles and the model that were used during this experiment, Newton's second law is F net equals ma. If F net equals 0, then the acceleration equals 0. If the acceleration equals 0, then velocity stays constant, and constant velocity motion equation equals x equals x naught plus velocity times time, which predicts a straight line on the position versus time graph. The systems and assumptions for this lab were the systems were the marker being rolled across the table, the surroundings or the table, the air, gravity, and the phone. And the assumptions are that motion is one-dimensional, the camera is stationary, friction is small/negligible, velocity stays constant, and net force is pretty much equal to 0. The experimental setup is we recorded a video of the marker moving in a straight line with a meter stick in the background for calibration. Then we imported this video into Tracker, marked object position frame by frame, and then Tracker generated position and time data, which is shown in this image here. Tracker data results, we extracted the position versus time data, plotted a graph in a spreadsheet on Google Sheets. The graph is approximately linear and the slope gives a constant velocity, which you can see in this graph to the right. This indicates that acceleration is pretty much 0 and motion is constant velocity. The computational model was a built model in GlowScript. We used Newton's second law to update motion step by step. The model logic was set acceleration equal to 0 and set velocity as calculated from tracker data results, which we did doing the position of one point minus the position of another point divided by the time of that point minus the time of the other point, which we found to be 0.343 decimeters per second, and then update that position as time continues. The top right shows the position vector to equal 0 and the velocity vector to equal 0.343 decimeters per second, and then zeros in the other two directions because motion was linear, while the bottom image shows the position being updated with each passing 0.01 second. Model versus experiment comparison, plotted both data sets on the same graph, or different graphs in this case. Tracker data equals points, the model prediction equals the line. The two graphs overlap closely, showing that the model accurately predicts real motion and confirms that constant velocity and 0 net force. The additional questions, one being, what if the axes were flipped? The slope would become negative and direction changes sign. The speed magnitude stay the same and the physics do not change. The only thing that would change would be the direction. What does 0 net force mean? It does not mean that no forces exist. In this case, gravity is still pulling our marker down, but it means that multiple forces can cancel. In this case, the normal force of the table pushing up against gravity pulling down, and the small friction is canceled out with pushes from the table. Their sums all equal 0, which means that the acceleration equals 0, which means that there is constant velocity. Any sources of error would be tracker marking inaccuracies, calibration measurement uncertainty, camera angle distortion, small friction or air resistance, timing/frame rate limitations, which explain the small differences between the model and the data. And the conclusion is constant velocity is in fact